I have here a neat little device. It's a laser, little keychain laser, and you've probably seen these by the time this video comes around. These things should be fairly common. And if I turn on the laser, of course I can get the usual dot, the kind of dot that you use in a laser scope where you're trying to aim a gun or some kind of projectile fire. But there are other things that we can get. Okay, from the same laser, I simply turn the top of the laser and I get this pattern. Now that's kind of important pattern. Notice how it's brighter at the middle, and then you have this place where there isn't much going on, then it gets brighter again, then it gets dimmer. Okay, that's a pretty important pattern, and that keys us off to the fact that we have what's called interference going on here, and we're using something called diffraction gratings, and we'll learn about those later. We have a circle, okay, perfectly nice circle, except there's a dot at the middle. We can't seem to get rid of that dot. If I move back further, you might see that the circle is formed from a lot of little dots. Let's hold it still and see if you can see that. You might not be able to see it. Here's another pattern, a star. Okay, formed of dots again. If we come in closer, of course, it gets brighter. More energy concentrated in a lesser area. Right there is a Valentine's Day greeting. Again, if you look at it closely, you can see it's made of a bunch of little dots. Now, how are we doing that? One thing you notice is that in close or out far away, this image stays pretty constant. It just gets bigger or smaller. And I'm not refocusing anything. I don't have a lens in here to refocus. How's this happening without a lens? How do we get these images out of one little laser? Okay, that's an interesting question. There's some interesting answers to that question. When we study, going the wrong way here. Again, this is a one-man show, so let's do the best we can here. Okay, that looks pretty good. I have to look over there sometimes because that's where the monitor is, and I have to make sure everything's centered and so forth. Forgive me for not always looking at the camera, and forgive me for sometimes looking down at my notes here, but I want to be sure I cover everything. What you saw there is a wave phenomenon. Okay, there are other wave phenomena. Lenses give you a wave phenomenon. The lens that's focusing me onto the receptors in the camera that then print the message on the videotape and so forth. Those lenses are optical devices. They change the direction of light by refraction. How do lenses work? If we move a lens further away from a source, the picture goes in or out of focus. There's only one distance at which the lens focuses. If you change the distance, you have to change the focal length of the lens. What's going on there? How do we get an idea of the difference between what you just saw with the laser and what happens with lenses? Okay. Other things that we study with respect to waves, because these are all wave phenomena, are things like Doppler shift. An engine comes toward you, a train comes toward you, it's got a higher pitch, or it sounds like it has a higher pitch than when it goes away. If it's blowing its horn, the horn is high, then it's low. Where does that come from? How do we develop musical scales, and how do we get the harmonies that we recognize as music? How do we perceive the intensity of a sound or the intensity of light? Okay, sound and light are both wave phenomena. You can describe a lot of the same things. They're described by a lot of the same mathematics, a lot of the same physics, a lot of the same concepts. What about energy? The energy of a set of speakers, the energy of a light source. And why does light, or why do wave phenomena, sound, light, other wave phenomena, dissipate? Okay? These are really interesting and really important questions, and hopefully we'll come up with some good answers to these questions in the course of this second semester physics class.